causal treatment, no matter how good your model is, you could have the best model in the world, but what models do is they're leveraging associations. They're taking what they can understand about associations and they're making predictions with those. But they say nothing about causality. And sometimes when we want to make a decision, we really need to know, does A cause B? Because if it doesn't, then I need to maybe not make a decision. But if it does, I want to go ahead and do something else. So I need to know if I've got causality. To establish that, there's one gold standard, and it remains one gold standard, and that is a properly designed, controlled experiment. We can't always do that. We may not have the money, we may not have the time or the material anymore. Maybe we've got historical data, but we don't have the material to do new experiments. It could be illegal. If I'm working on human or animal subjects, there's many things that I can't do that a designed experiment would ask us to do that we just simply can't do. And so in these cases, we can still get the same insights and confidence in causality that we would have in using a designed experiment if certain conditions are met with our data, if our data can be arranged in a certain way. And that's what this platform helps us understand. It tries to assemble the data in that way, and it will assess how successfully that happened. And if it did happen successfully, then we can make causal inference the same as if we had done a designed experiment. So let's take a look. In this particular example, we're talking about a drug, and the treatment is the new drug, okay, and the control is the old drug. And you can see I've got a lot more people involved with the new drug than the old drug. What I'm measuring is, does this new drug reduce blood pressure more effectively than the old? And so how I'm going to measure that is the post-treatment blood pressure. I'm going to subtract that from the baseline blood pressure. Let's look at how we would do this in the past. What are the typical things we're going to be able to do? Well, one of them is to look at, what happens to this distribution across various levels of other variables. And if I'm going to do something right here. I want you to look right here at this 14.92. That is the mean of this column. That's the mean drop over the whole data set. But as I select things here, that mean's going to change. And so if we look at the treatment group, that mean is 16.47 for them and 7.10 for the baseline group. So that's encouraging. And we can see that over here looking at these distributions. You can watch that mean shift down. So, okay, that's interesting. Let's look elsewhere. What's going on? Okay, diabetes or not. Yeah, it's a shift, but not so big. These all these shifts are within one or two. They're not a huge shift like we were seeing for treatment. So this is all encouraging. We want to make sure our validation and training sets were stratified properly, and they look to be, if I look at age, high age, 1794, low age, 1399. Yeah, there's a difference. So that's, three or so. So age is probably important. BMI, 14, 15 and a half. So there's some effects here, but they're nothing like, we're not seeing anything like we saw with the, physical activity. It's important. Uh, so there we have it. None of these were really as big as we saw with the treatment. Not even close. Not even half as much. Age and physical activity looked important. We could confirm that with a predictor screening, and it's showing those same things as being important. So everything looks, it looks as if, I run a model on this, I run a lasso, and yeah, it says these, using the treatment drug is 8 points better, 8.5 points better on blood pressure. But again, that's all I can do. I can't say there's causality. And that's where we used to have to stop. We just said, yeah, it sure looks good, but we got to stop here because we just couldn't know if there was confounding due to the way the data was structured. Well, now it's pretty easy to find out, is there causality? I can come to the fit model platform, and at the bottom here, causal treatment, put my treatment in the treatment category. I'm going to model the post-treatment systolic blood pressure. And then things that are confounders, I'm just going to put in here. So certainly the baseline blood pressure is a confounder, along with all these other guys here. Those are potential confounders. And let's go ahead and hit run. Now there's different models we can run, but I'm going to run one that I should be able to explain well is the nearest neighbors approach. And what this is trying to do is it's going to take somebody from, each group and try to match them up if they look similar. So, ideally they'd be the same age. They would have the same value on all of these or close to the same value on all these other confounding variables like you would see in a designed experiment. And so I'm going to not match with replacement here so that we get the following result. First thing that comes back is it's a 166 row table. That's telling me there's 83 pairs. Okay, and so here's the first pair, and I can see, well, how do they compare to one another on all these variables? And so that's really nice is it's showing you how things were matched up and so that you can dig deeper and find out, well, were these matches really that good? Do I have any problems with the way things were paired up? We've got the diagnostics in the report to help us understand, what does it look like is happening here? So I can add some points here if I want. Look at those, certainly it does look like the treatment class has a lower result than the control. Here's a assumption check, and what you want to see here is you want to see these distributions on top of one another. If they're separated from one another, that's telling you, in a nutshell, that the way the data is structured, it does not afford a good way to structure this like a designed experiment. The further apart those are, interpretation is, it's suffering. You can't be as confident that there was actually causality, even if the model shows an effect. The other thing is when we adjust using this inverse propensity weighting scheme, we want to understand, well, did that do a good job to balance out the covariates? And you can see the red squares, they're kind of all over the map, and some of them have really high values. But after the adjustment, these blue dots, you want to see them all under about 0.05. And, most of them are well under that. And even the worst one is at 0.0518. So that is all looking good. And so what this is telling us is that everything's looking good for us to be able to make a conclusion of causality if the model supports it, if the estimates do. Here we've got a graph where we can see, okay, where was the region of support? We want to see a good region of support over the matched observations, and we do. And this is showing us, okay, the treatment and control groups, who was matched with whom as plotted against the propensity scores. So this all looks great. I mean, bottom line is we will be able to conclude causality as long as the model bears that out, and it does. We've got high significance, and we've got a good effect here. The treatment, which is about what we found earlier, a little bit less, but it's about 8.3 points lower for the treatment, the new drug. And so this is huge. I mean, it is a big deal to be able to conclude something like this without a designed experiment. And so think of the historical data people have and the decisions they might be able to make. And they may have been wishing to do a designed experiment, but they just couldn't. It's not like these are new methods, but the number of people that could do these analysis, there's not a lot of people that can. It requires a lot of training. And so to have a piece of software that's able to lead you through this and give you the diagnostics, that's what the big deal is. It's hard to overstate how valuable this could be. So if you have any interest in all, you should definitely check this out.